Welcome back to the Foundry by Forge College. Listen, right off the bat, I just want to say a massive congratulations on the hard work you put into our previous lesson. Seriously, calculating those complex Gini coefficients and really dissecting all those decentralization trade-offs, that was no small feat. But hey, you made it. And today, we're going to take all that raw abstract data and actually put it to work. In today's explainer, we are officially gearing up for your capstone project, evaluating consensus mechanisms. Our main goal today is to lay out the groundwork, build our blueprint, and basically figure out exactly how we're going to measure and judge these incredibly complex blockchain systems without, completely losing our minds in the process.
So let's just dive right into the core problem here. In the wild world of Web3, we have vastly different consensus mechanisms, right? You've got your classical Byzantine fault tolerance, your Nakamoto-style proof of work, your delegated models, and they are structurally completely different beasts. If you try measuring these drastically different systems without strict, consistent criteria, your capstone report isn't going to be a rigorous analysis. It's going to end up looking way more like a messy, abstract art collage than a controlled scientific experiment. We really need a solid way to compare an apple to a decentralized orange, fairly and accurately.
Here is our blueprint for today's explainer. We'll start with the assembly line metaphor, then define our evaluation criteria, learn to compare apples to apples, map out our one-page project plan, and wrap up with next steps.
All right, Section 1, the assembly line metaphor.
Okay, to keep us from getting totally bogged down in abstract technical jargon, I want you to visualize a bustling factory floor. Just picture a conveyor belt that's constantly moving, and along it there's a sequence of inspectors and quality control gates validating raw parts before they finally drop into the finished product bin. This really simple, tangible image, this is our Rosetta Stone for decoding complex consensus mechanisms.
And the cool thing is, we can map this factory floor perfectly to a blockchain network. The raw parts, those are our transactions. The inspectors holding the clipboards are our validators. The protocol rules act as our security gates. And those adversarial actors we always worry about, they are literally just noisy rogue tools trying to slip defective parts past our gates or just jam up the belt entirely. When you start thinking about it this way, evaluating a blockchain is really just evaluating how smoothly a factory runs.
Moving right along. Section 2, defining evaluation criteria.
Now that we have our factory laid out, we have to translate those assembly line checkpoints into actual explicitly measurable criteria, usually about 4 to 6 of them. For instance, safety ensures defective parts don't get through, which means we mathematically prove that if less than a third of our inspectors are corrupt, the factory stays completely safe. Liveness simply asks, does the belt keep moving? We measure that with uptime. Performance is just your conveyor speed, or TPS. And decentralization? That ensures we don't just have one giant inspector bossing everyone around, but rather a widely distributed team.
Remember those Gini coefficients we agonized over in the last lesson? Well, they form the absolutely critical baseline measurements for our decentralization criteria right here. A Gini coefficient of, say, 0.44 for a BFT validator set tells us exactly how the stake, or the power, is distributed among our inspectors. If just one slice of this pie gets way too big, boom, our factory has a single point of failure. By sticking to these precise metrics, we move away from vague qualitative opinions and start making hard, testable assertions.
Next up, Section 3, comparing apples to apples.
But wait, before we write our plan, we absolutely must ensure our comparisons are actually mathematically valid across entirely different consensus families. You can't just compare raw numbers. Take finality, for example, that exact moment a transaction is permanently carved in stone. On one hand, you have deterministic finality, which is measured in milliseconds. The gate slams shut and it is done instantly. On the other hand, you've got probabilistic finality, measured in minutes. It's more like parts falling into a bin. The deeper they are buried, the more mathematically certain we are they won't be removed. Trying to compare milliseconds to minutes is literally like comparing a microwave to a slow cooker. I mean, sure, both get the job done, but the math is totally different. We need to translate both into a comparable risk of reorg metric.
So how do we fix that? Through normalization. Normalization is the great equalizer here. It takes that raw, totally incompatible data and transforms it into a standardized format. By converting raw measurements into a common scale, think z-scores or percentile bands, you can suddenly say how extreme a value is relative to the rest of the group, rather than just pointing at raw numbers. This is what guarantees that your capstone judgments remain completely auditable, statistically sound, and above all, fair.
Moving on to Section 4, the one-page project plan.
Now we're in the execution phase. As you know, Forge College learning programs consistently emphasize structured, auditable workflows. The first half of our 7-step process focuses heavily on defining your strategies and actually confirming that they work in the real world. Step 1, finalize your criteria. Step 2, define that normalization strategy we just talked about. Step 3 is your data collection plan, like where exactly are you pulling this data from. And Step 4 is absolutely crucial. Execute benchmarking and test runs. Please do not wait until the final project to find out your data access and query scripts are completely busted. Manually confirm they work on a small sample first.
Then we bring it all home with the final steps. Step 5 is drafting your rubric and clear acceptance thresholds. What exactly counts as better, comparable, or worse for your factory? Write it down. Step 6 guides you to assemble all this into a concise one-page plan. And finally, Step 7, peer review and iteration. Run it by a colleague. If they look at your plan and don't immediately understand how you're measuring these systems, well, you need to refine it.
When it's all said and done, your finalized blueprint should look exactly like this clean one-page layout. You've got a clear header, a left column for criteria and metrics, a center column for data sources and normalization, and a right column for timelines and acceptance checks. This gives you an easily readable, at-a-glance blueprint for your entire capstone project.
And finally, Section 5, Next Steps.
With your factory blueprint drawn up, it's time to set up for the next phase. Before you jump into the next lesson, which, by the way, is a deep dive into comparative analysis of Byzantine fault tolerance, you've got a little homework. I want you to finalize that criteria checklist and pull at least one sample data point. Grab a reorg count, or maybe do a 24-hour TPS extract, or calculate a single stake snapshot. Just bring that actual, real-world data to the table next time so we can put this blueprint into immediate action.
So, I'm going to leave you with this thought. If just one of your factory inspectors goes completely rogue, does your entire decentralized system crumble? Think about how robust your metrics really need to be. Get out there, build that perfect one-page plan, and be sure to visit forge.college to learn more about this subject and catch other deep dives into Web3 topics. I will see you in the next explainer.